There, this is the video for section 6.1 on how to find the area between two curves using integration. A couple quick disclaimers before I get going with the examples. First is, remember, we're going to be slicing the region into infinitesimally thin or small rectangles and writing down the differential that represents the width of the rectangles. You can do most of the problems in this section just by using a formula and putting things in, and that may be tempting to some people, but the idea of this section is to start understanding the technique of slicing something into infinitely thin rectangles and then trying to find a way of summing it up. As we progress to more complicated concepts in this chapter and in future chapters, this idea of slicing, finding the area or the volume or the surface or whatever we're looking for, and then adding it all back together is a very difficult concept, especially with these more esoteric ideas that we're combining together. So my advice is to try to resist just relying on a formula. Try to build up the understanding of the concept of how we slice things together, because those future sections will become a lot less frustrating if you understand the technique instead of just relying on a formula. And as we go along, the formulas just don't work anymore. So we have to understand the technique to be able to get the correct result. All right, so with that out of the way, let me get going showing you some examples and showing you how this sort of technique that I'm talking about works. My first example here is to find the area between this y equals 3 over x function and the y equals x squared minus 8x plus 16 function from 3 to 4. I do recommend that you make a graph of these things. Most people will benefit quite a bit just by seeing what's going on. So I'm going to use Desmos. And I've typed in a bunch of graphs here already. The 3 over x and the x squared minus 8x plus 16 are right here. And so this is the standard graph that Desmos will give you. And just to remind you, no matter what device you're using to help you do graphing, the hard part is not typing in the equations. The hard part is trying to find a good viewing window. And looking back at this problem, if you have the lecture notes, you can read along. It does say from x equals 3 to x equals 4. So that's really the only place we're interested in looking at. So if I kind of think about the fact that 3 and 4 over here, I need to zoom in a little bit. And there's the 3 to 4. In fact, I can go to this little wrench up here in the corner, and I can literally type in 3 and 4, just for the x minimum and x maximum values. And that's the 3 to 4. I find it a little bit too close up. So, I'd recommend zooming out a little bit, but there's your 3 to 4. You can also literally put 3 and 4 into Desmos. So it'll say it's between here and here, right? It's this shape right here. So you can kind of see it there. It's sort of, I don't know, triangular, curvy, something like that. So that's the region we're trying to find the area of. And what we're going to do is we're going to be slicing this into really thin rectangles. The first rectangles I'm going to be doing are going to be vertical, but we can also do horizontal rectangles. So I'll be showing you some of those as well. All right, so this point right here is actually where the two graphs cross. It's at 3, 1. Over here we have like a 4 3/4 or something like that. So it's this sort of weird graph. I'm going to try to roughly draw it. I don't, if you're doing your work, especially if you're doing a lab or a test or something where you have to show your work, I don't recommend like you making it look perfect, but we have an XY axis. We have 3, we have 4, we have 3, 1, we have 4, like 3/4. This kind of goes down and down and down, right? And the top graph, if you want to know what the top graph was, if you click on the top graph, you'll see that this one lights up, 3 over x. And if you click on this bottom graph, you'll see this one lights up. So the 3 over x is on top. So, for your A plus student, you might write something like 3 over x is the top graph. Nope, I didn't write the bottom graph, did I? Yeah, there's a bottom graph like this. So I need to do the bottom graph as well. They both intersect here and it goes down like that. Okay, something like that. It doesn't really have to be like perfect. I just wanted to get somewhere close to there. So the 3 over x graph is on the top. And then the bottom graph here, or I guess I'll do it over here. The bottom graph here is the graph of the x squared graph. All right, and we're trying to find the region in between, and the region, remember, is not this one down here because it's between the two graphs. So here it's between the purple graph and the x-axis, and it doesn't say that. It says between the two graphs, the blue and the purple graph here. So I need to have this area here. So it's this area here. Okay, so I'm going to get rid of this little blue line over here because it seems to be distracting me a little bit. And then I'm going to try to find out like how to find the area of this thing. All right, so that's the region there. If you want, you can make it bigger with less detail. It's up to you how you want to do this thing so you can see it. But that's sort of the region in small and bigger. And we're going to be slicing this. And the first thing I said, the first types of problems I said, we're going to slice it vertically. So here's a vertical slice. And it should be really, really thin, infinitesimally thin, although we can't do that with a, an actual, object, but pretend it's infinitesimally thin. Okay, that forms a rectangle. It has a long, height. It has a very, very small width. The height is in the vertical direction, so that's a measurement in the y direction, and the width is in the x direction. An infinitesimally small change in the x direction is called delta x or dx, right? Delta x is the one where we say it's a finite change, dx where we say it's an infinitesimal change. And this is some y height that we need right here, right? So we need a y height for here. And then what we're going to be doing is we're going to be adding up all the possible y dx heights. There's, one of them right here, which is super, super small. At least the height is very, very small. And then there's one over here. And there's all the ones in between. So the area is going to be the area of one little rectangle, y times dx, right? It's the y height. Well, let me not write y yet. Let me actually figure this out. But I'm going to be figuring out the height times the width. And once I find the height times the width, I'm going to be adding them all up, which is the integral. So height times width is the area of a rectangle. I need to add them all up, and I need to add them up from x equals 3 to x equals 4. Okay, so what is the width? Well, the width spans from the 3 over x. Let me draw it over here on our diagram that has labels on it. The width here is our span from 3 over x, not down to the x-axis, but down to x squared minus 8x plus 16. So how do you find the distance between two things, right? So how do you find like the distance between two objects? You subtract. Like if one person has $20, another person has $4, what's the difference? What's the, the change between those two? You just subtract, right? So it would be 20 minus 4 or $16. In this case, you're subtracting functions. So the height is going to be a y height, but it's basically your y big minus your y little, right? It's going to be a difference of two y things. And the width, as we said, is super tiny in the x direction, so it's dx. So this ends up being an area of, let me go back to black, of x equals 3 to x equals 4. The big one is 3 over x. The small one, the little one, is x squared minus 8x plus 16. Don't forget your parentheses. And all of this is times dx. And that's the setup for the area of this region, right? You get the y height, which is really subtracting two functions, times the width, which is this dx. And the rest of it's just mechanical, doing your integral calculus thing. There's not much going on at this point, but I will go through the last steps just to make sure we finish the problem. All right, so I need a little more space there. So I'm going to simplify it first. And I'm going to just write 3 and 4 here because we now know that it's x values. The key thing that's important, the key idea for all these problems is that the differential dx has to match all the other variables. So this is 3 over x, this is x squared, this is 8x, doesn't have an x, and here's an x here. So the dx is the guide. All the variables in the problem have to match dx. I cannot write y here and y here and do any math because the variables don't match dx. So you can put some y's in there. I find it very helpful, but until everything is the same variable, you can't really do much. You may remember that from the integration by substitution review that you did in the previous assignment. All right, so I will just distribute the minus sign for this simplification. So 3 over x minus x squared plus 8x minus 16. And all this is times dx. And because these are added or subtracted together, I can just do each one separately. The integer of 3 over x, 3 is a constant, so it does not affect, it's a constant being multiplied, so it doesn't affect the antiderivative. So it's 3 times whatever the antiderivative of 1 over x is. The antiderivative of 1 over x is just ln x. Antiderivative of minus x squared is minus x cubed over 3. The antiderivative of 8x is 8x squared over 2, or 4x if you prefer. And the antiderivative of 16 is minus 16x. And there is a constant of integration, but because we are evaluating this at 2 limits, the constant integration will always undo itself. You always have a plus c and a minus c. So most people just don't even write the plus c when they're doing an integral where you're plugging in numbers because they're just going to go away anyway. So we're going to plug in x equals 3 and x equals 4 and subtract them. And now it just becomes like a calculator problem, right? You have to plug in 4. So you get 3 ln 4 minus 4 cubed is 64 over 3. And then plus 64, 8 times 4 squared is 8 times 16. I'm not sure what 8 times 16 is in my head, but 8 times 16 over 2. And then minus 16 times 4, which is 64, I think. And that's just when I plugged in 4. So this whole thing is subtracted when I plug in 3. So then I get 3 ln 3, etc. Right? I don't need to go through all the arithmetic for you. I don't believe. At this point, I think our time is better spent doing calculus stuff than just doing all the arithmetic stuff. So that's x cubed over 3 when x is 3. Oh, it's not 27 cubed, sorry. X cubed is 27. So let me just write this so it's not an error so that people will not get the wrong answer when they're copying what I'm doing. X cubed over 3 is 27 over 3, and this is plus 8 times 9, which is 72 over 2. And then finally minus 16 times 3, which I think, yeah, it's 48. Anyway, and then you just plug that into a calculator and get your answer, which, as I mentioned, I'm not going to spend a lot of these video times doing calculations. I just don't think it's a great use for our time here. I want to move along to the next example. Okay. So let me zoom out a little bit so you can see the full solution. All right. So got an idea of what it looks like. Used a rectangle to divide it up. Found the dimensions, the height and the width of the rectangle. And then I added them all up using integral. And then I did the math. All right. So the rest of them are going to be kind of similar to this. But like I said, I'm going to show you some where we're going to do horizontal rectangles instead of vertical rectangles. So you can see how that kind of works. Let's just do a couple more examples so you can see these in action. All right, so example B here, I have a couple of functions here. This is a different one, negative x squared plus 8x plus 6, and this is y equals x plus 4. And it does not give from x equals 3 to x equals 4. So you may notice on the first problem, I put the limits 3 to 4. So we knew to put 3 and 4 on these limits right here, right? That told us we had to go from x equals 3 to x equals 4. This second problem I made up has no limits. It doesn't say x equals 3 to x equals 4, but it does say between these two functions. So let's try to figure out what we can do with that one. So x plus 4 and x squared minus things. So I'm going to get rid of this thing here. And then up here, I believe I have x plus 4 and the other function right here. Now, you might not be able to see anything, but again, that's because the hardest thing about doing these graphs is sort of knowing what the picture looks like, knowing what the window looks like. So I can scroll out a little bit, or I can hit the home button and I can just zoom to home. Oh, it didn't erase the other graphs. Let me get rid of these other graphs. Sorry. Boom. So here's the two graphs. The one in green is x plus 4, and the one in red is the x squared graph. And it says between the two of them. So just by looking at this graph, I can even zoom out. There's only one place which is between the two graphs, and it's this one right here, this little sort of half circle cup thing here. So that's the part they were talking about. It goes from this point, which is 2 comma 6, to this point, which is 5 comma 9. So we have a graph going from 2, 6 to 5, 9. And there's a parabola and a straight line type thing. All right, so for this guy, I'll do my XY axis. Maybe move it up. I'll do my XY axis. I had 2 comma 6, which was here. And unfortunately don't have a short-term memory. The other was 5 comma 9. So I'll pretend 5 is over here and 9 is up here. And boom. And we had like a parabola looking thing. And we had a straight line looking thing. And our region is there. You may see a lot of mathematicians put an R in the region just to identify that. I don't do that because I don't do it often because I can't draw my rectangle in there. So let me go ahead and draw my rectangle instead. I just have to go a rectangle which is representative of that region. So, any right here rectangle, remember infinitesimally thin if possible. The rectangle goes from the curved parabola part down to the straight line part. And that's true even over here with this little teeny height rectangle, all the way over here, which is also a teeny height rectangle, and everything in between, all these other rectangles, they all go between, on the low graph, the line x plus 4, on the high graph, the negative x squared plus 8x minus 6. So here's the y equals x plus 4. And here's the y equals negative x. I'm going to show you a trick so you don't have to write so much. This is going to help some people, I think. But like, okay, so what's the order with this? We just call this one f of x, and we just call this one g of x, and then we don't have to write the whole equation anymore. So this is f of x down here, and this is g of x up here. So these weird function things, they do have some uses because you can distinguish the two of them just alphabetically. Okay, so those are my two things. So what is one little slice? One little slice here has a vertical or a y distance height and a horizontal or an x distance width. So once again, we're going to have the area is equal to the height times the width. I'll just do h times w. And then I have to integrate all of those. And I'm using a width that's in the horizontal direction. So the width here, that little width here, is called dx. So because my width is dx, that means everything else has to be in terms of x's. So area equals. So these limits on the integration have to be the limits in terms of x's. So what's the smallest possible x? It's 2. And what's the biggest possible x? It's 5. So we know the limits here are x equals 2 up to x equals 5. All right, and then all we need to know is the height. And the height is the vertical distance, which goes from the top one down to the smaller one. So to find the distance between two things, we just subtract. So we're going to get something like, a y big thing minus a y small thing. I kind of crammed it in here, sorry. So you're gonna have to subtract two y values. We have to put it in terms of x because once again we have a dx. Everything has to be in terms of x. All right. So we already know the top function is that g function or the x squared function. So this is going to be the integral from 2 to 5 of the big y version, which is the parabola looking thing, minus the small one, which is the line looking thing. Notice I'm just using parentheses to mess up with the negative signs. And then all that stuff is times the width, which we know is dx. So we've reduced this problem of trying to find the area between two functions into just a regular integral problem. So again, this is just a more mechanical part of the process. There's not a lot of new math going on here. If you're familiar with antiderivatives from Calc 1 or from reviewing in homework earlier, this is just another one of these problems. So the first recommend is to simplify things. So I'm just going to remove all these inside parentheses and combine 8x minus 1x is 7x. So I got minus x squared. 8x minus x is 7x. Negative 6 minus 4, whoops, x. Negative 6 minus 4 is negative 10. And then this is times the dx. And then I just anti-differentiate stuff, antiderivative of negative x squared. You've done that a few times, I think. This is going to be 7 over 2x squared minus 10x, and then plus a constant. But because we're evaluating at two numbers, at an endpoint 2 and an endpoint 5, it becomes irrelevant whether I have a constant there because I'm just going to get a plus c and a minus c, and those always add to 0. And now I'm going to plug in the 5, and I'm going to plug in the 2, and then I'm going to do the math. Or maybe you'll do the math because I hate doing all this arithmetic stuff, as you can probably tell. So I'm going to get 1/3, and then they plug in the 5, and then you're going to plug in the 2. So it's that whole thing minus when I plug in the 2 to the exact same expression. And then it just becomes like a big, number crunching problem. 7 over 2 times 2 squared, which is 4. Oh, that's right, 2 squared. And then minus 10 times 2. So just do all the math out for that. You get an answer, and that is your area. Sorry if you really want to have an answer. I have belief that you can put this into a calculator and get a number. And if you do make a mistake putting the calculator, that's not really calculus. That's just arithmetic on a calculator. So slow down, be more careful if you don't get the exact right result, and then you will. So I really wanted to focus on how to cut this region into rectangles with an infinitesimally thin, dimension, in this case, the width, and then how to find the area with that methodology in mind. Let me do one which is a horizontal slices, so you can see what that looks like. So this one, I have the equations written as x equals, which is a good tip that you're going to be doing horizontal slices because everything is already written in terms of y's. And I'm going to show you on the picture also why that's helpful. So this is 2y squared and y cubed. So I'm going to get rid of these guys. And I just typed in these a little bit ahead of time to save time typing and stuff. So I don't see anything, but that's probably just because I need a better window. Oh, there they are. So, okay. So it has to be between the two of them. This one goes off, this one goes off. So it must be this little thin slice over here. So they start off here at 0, 0, and they end up over here at 8, 2. and they're like really close together. The one on top is the one you can see it flashing here, the x cubed one or the y cubed one, and the one on the bottom, you can see it flashing there a little bit. That's the 2y squared. So y cubed on top and 2y squared on the bottom, and it goes from 0, 0 to 8, 2. Okay, so let me just recreate that real quick. So 0, 0 right there, and 8, 2. I'm going to call this 8. I'm going to call this 2, like this. And we have, like, I'll do the right color here. We have one on top, and we have one on the bottom. And we know the one on the top is the fx function, and the one on the bottom is the gx function. So we have f on top, g on the bottom, like that. Now we could slice these vertically, there's no doubt, but I'm going to show you how to slice these horizontally and why that's kind of nice for this problem. So again, I'm going to make a rectangle. We're always slicing into rectangles. It has an infinitesimally thin like width, and it has some length there. So the length is in this direction. That's the x direction. So this length is going to be something about x's. And the width is in the vertical direction. The width, is this little span in the vertical direction. Vertical direction is measured with y's. So a very small change in the y direction is called dy. So we're trying to find the area, which is, again, just the area of the length times the width, right? Just the standard formula for a rectangle. The width is dy, right? The infinitesimally width there is in the y direction. We call it dy. So that means we need everything else in terms of y, which means we need the limits of integration in terms of y, and we need the length in terms of y. So the limits of integration are in terms of y. What's the smallest y and what's the largest y? You can kind of see it on the picture there. Smallest y is 0, and the biggest y is 2. So that's how y goes from the lowest rectangle down here to the very highest rectangle down here, and all the rectangles in between. They all go from y equals 0 to y equals 2. And then we need to have the length of this rectangle. The length is a horizontal length, and it's between two things. And to find the distance between two things, you subtract them. We got to do the bigger one minus the smaller one. So bigger in this case isn't vertically bigger, it's x bigger, which has a bigger x value. So you can see that from this little slice I have here, the one here on the right is the bigger x value, and that's the g function. So it's going to be the g minus the f. That's the two functions I have to subtract, but I need those in terms of x values, right? I need the x for the g function and the x for the f function. G minus f looks to a math person like they are y values, because they usually use like g and f to represent y values, like g of x and f of x. So to make things much clearer, why don't you just say x for the g guy and x for the f guy? Then I think that communicates much clearer. We're subtracting x values. We're doing the g thing minus the f thing. All right, so now we just need to do substitution here. We need everything in terms of y's because this is a dy. So what is the g function in terms of x? That's this guy right here. So that's 2y squared. And then we need xf, the f function, x direction, and the f for the f function, which is just y cubed. And then, of course, we have our dy. And that, my friends, is the integral. So we just anti-differentiate, plug in the numbers, and you're good to go. I'll do another anti-differentiation because I know some people really like to see it. But I think for most people, and even those who want to see it, I think you kind of know the rest of this problem. I think you got it. So we got to anti-differentiate 2y cubed. The 2 does not change. It's a constant being multiplied. The antiderivative of y squared is y cubed over 3. The antiderivative of y to the third is y to the fourth over 4. And then to find the area, we use the fundamental theory of calculus, which means you plug in the two endpoints and subtract. So I get the area is 2 times 8 over 3 minus 2 to the fourth is 16 over 4. So that's when I plugged in the 2 value. And then I'm going to plug in the 0 value, 2 times 0 over 3 minus 0 over 4. So the other one's just 0. And so we get the area equal to whatever this works out to be. 16 thirds minus 16 fourths. I'm sure we could do it, but I'm going to go on. So hopefully you're getting the idea of how this works. All right, so I'm going to do one last problem for you in section 6.1, and then we'll be done with this video. So example D, I tried to make a little trickier. They are functions y equals x minus 6 and y equals cube root of x. I'm going to put those into a calculator. So here's y equals x minus 6. Remember, cube roots are the third exponent, so I use the third exponent here. And that's the thing right here. So what region are we talking about here? Let's go look at the problem again. Oh, and y equals 0. So I have to graph y equals 0. So y equals x minus 6, y equals cube root of x, and y equals 0. So let's throw in y equals 0. Oh, here it is, y equals 0. All right, so I need a region that's bounded by all three of those. They gave the region for 3 things, so I can't just look at 2 of them. So I have to look at all 3 of them. And you may be seeing what I'm seeing now. Here's the one down at the bottom. That's y equals 0. That's the purple one. And then we have a blue one, and we have a green one. And it makes this shape right here. It has to be bounded by all 3 shapes. And that's the only one which is bounded by all 3 shapes. This one right here is unbounded. It just goes on forever, right? There's no other place where it's actually bounded by all 3 things. So that's the first tricky thing about this, is that you have to figure out what region we're talking about. And reading the problem carefully and writing down the 3 functions is going to be useful. So this ends over at 8, 2, starts at 0, 0. So 0, 0 to 8, 2. And we also have this 6, 0 thing. All right, so let me sketch that real quickly on my notes so that you can see that I'm using a picture as part of my solution process. Remember, you want to document your process. 0, 0, 6, 0, and 8, 2. Zero, 0, 6, 0, and 8, 2. And then it went like this. And then I think it went like this. And then I forget which it was, concave in or concave out. It's kind of going bowing out a little bit. So kind of like this. So that's our region right there. And I'll do this one as F, this one is G, and this one is H. So F is this one on the right here. G is this curvy thing over here. And H is the sort of the bottom right there. So that's our region. And we're going to slice this. Now, a lot of students default to slicing vertically, right? So let's do a vertical slice. So we got a vertical slice right here. With a vertical slice, our width is dx because it's very small in the x direction, and it goes between G and H. So if I want to find like how high it is, I just subtract G minus H to find the height. And I'm going to be adding up all the rectangles as far as we go, which means from over here on the far left rectangle, which is a very short rectangle, all the way over here to the side. Those are all the possible rectangles and all the ones in between. So those are all the rectangles we need to add up. Now, some of you actually may have noticed something. These rectangles here on the right, they go between the G function and the F function. For example, this one right here, it goes from here, which is a G function, to here, which is an F function. So to find the height of that rectangle, I would do G minus F. But we said over here, for this rectangle I drew originally, that would be G minus H. So this problem is more difficult with a vertical slice because it changes. You'd have to break this up into essentially 2 problems. One problem going from like 0 to 6, where you're subtracting G minus H, and then another problem going from 6 to 8, where you're doing G minus F. and then you would find the area of those two kind of parts and then add them together to find the total area. You can do that and it will give you the right answer. But I wanted to show you that a horizontal slice is actually much easier for this problem. So that was kind of the thing I set up for this problem, is that you want to actually keep your flexibility there and say, I can do horizontal or vertical, whatever I think is easier. So a horizontal slice would be, well, a horizontal rectangle. The width is vertical, so we're talking about dy width. And we need all the possible rectangles. So the bottom, this rectangle is from here, and the topmost rectangle is here, and all the rectangles in between. And you may notice every single rectangle goes between F and G. There's no like two different problems to split it up into. We always do F minus G, the X direction, the X and the F, the X for the F function minus the X for the G function. So that's what we're going to do. We're going to do a horizontal slice here. So area is equal to the length times the width. So L times W. We're going to add it all up. The width is, in these horizontal slices, the width is dy because it's a very small slice in the y direction. So we're going to put a dy over here for the width. And then the length has to be in the x direction. So it's like an x for the big minus an x for the little, or I guess the way I'm doing it for these lecture notes right now is like I'm writing in the function. So the x for the f function is the bigger one, right? Because it's more on the, to the right, and xg is, more on the left. So it's x for the f function minus x for the g function. So what is the f function? Well, this is the f function right here. So the f function right here is y equals x minus 6. But I need to put x in there. So what is x? Like, what do I put in for the x for that f function? Well, I just have to solve for x. I need to know what x is to plug it in. So I'm going to add 6 to both sides, and I get y plus 6, and that's what goes in for x for the f function. And I do the same thing for the g function. So for the g function was over here. It's y equals cube root of x. But I need to put x in there. So what is x? Like before, in the previous problem, it was already solved for x. So we knew x is already 2y squared, and x is y cubed. So before, it was x equals, and it was really easy to plug it in. Here, it doesn't have x equals. So we just do a little algebra. It's not that complicated. We just got to get x by itself. And we know how to solve these things. If it's a cube root of x, then I cube both sides, and it'll be x equals y cubed. And so the x for the g function is just y cubed. And then I can write out my integral. The x for the f function is y plus 6. And the x for the g function is y cubed. And this whole thing is dy. And then I just do my math, right? Oh, I need limits. I need limits on the integral. So my limits on the integral have to be in terms of y. I keep reminding folks this, like, because it's dy, everything's got to be in terms of y. So what's the smallest y value? It's down here at 0. What's the biggest y value? It's up here at 2. So this has got to go from y equals 0 up to y equals 2. Right? Once you know the dy or dx, you just look in that direction to see what the minimum and maximum values are for your region. Okay. And so I'll do a little bit of this, but I'm going to, again, leave the actual calculations for y'all who are completionists, so you can get an actual answer. And, if you want, you can ask me, or you can just go on Wolfram Alpha and double check your answer using that computational engine. So this would be y plus 6 minus y cubed. There's actually nothing really combined together. And then I would get integral of y is y squared over 2. Integral of 6 is 6y. Integral of y to the third is y to the fourth over 4. And then I plug in 0. I plug in 2. I plug in 2 first, plug in 0 second, subtract the 2, and that's what my area is. Now, of course, if you're doing a lab assignment, or if you're doing a test or something and you have a problem like this, You actually do have to do the computation. You just can't write what I did. I'm being lazy. I'm okay with not getting 100% credit as long as I'm trying to clearly explain this to you. But just a reminder, if you're doing something for points, do the computation and get the right answer, please. So you get the full marks for that problem. All right, well, hopefully this video has been helpful. I tried to show you the concept of slicing a region into infinitesimally thin rectangles in order to find the area of that region. Please reach out if you have any questions or comments or have any what if scenarios or have any other kinds of problems that you'd like to get help with, and I'd be happy to help you with those. All right, well, please enjoy your day, and I hope to see you soon on the next video.